Good afternoon, everyone. My name is Matthew Jocelyn, and today I'll be giving a presentation on air-cooled screw chillers. So what are air-cooled screw chillers? They're machines that generate chilled water to provide air conditioning to a building. They remove heat from processed liquid through a vapor compression refrigeration cycle. So what that means is the refrigerant is used to move unwanted heat between the evaporator and condenser, where the fans pull air across the condenser and disperse the unwanted heat back into the environment. They use a single or multiple rotor screw compressor. These types of compressors are generally used to accomplish a chiller range from about 70 to 500 tons. And these units are most commonly used on medium-sized buildings with a cooling load of 200 to 400 tons of refrigeration. They're typically installed on the top of a building to provide adequate airflow to the condenser fans, or because there's limited space. They can also be installed on the ground floor levels, such as this one. They might be closed off to restrict access or to maintain pleasant looks at the ground floor level. Um, but also because the compressor and the fans can generate a lot of noise. So by gating it off like this, it'll help restrict that noise and make the surrounding areas a little bit quieter. So who invented these chillers? The first centrifugal chiller was built in 1922 by Willis Carrier. His invention was supported by nearly 20 new patents and provided air conditioning to factory floors, office building, department stores, and movie theaters. His first installation was done in 1923 in the Stephen F. Whitman and Sons Philadelphia candy plant. The installation consisted of three 75-ton units, which we can see here, and it was one of many historic installations that led to what Carrier liked to call his own version of the Roaring Twenties. So as more and more chillers began being installed in theaters, they became really popular spots for people to hang out in. Oftentimes, movie theaters were the very first time that people experienced air conditioning. So here is a diagram of a air-cooled screw chiller and its main components. Today we're going to look at the compressor, condenser, expansion valve, and the shell and tube evaporator. So the screw compressor is the driving force of the refrigerant. It's ran by an electric motor and uses single or multiple rotors. Refrigerant enters on the suction port as a low pressure, low temperature saturated vapor, or for some compressors, it'll enter as a superheated vapor. That's going to be indicated on the blue gas right here. And the refrigerant exits at the discharge port in red as a high pressure, high temperature, superheated vapor. Usually the male rotor is connected to the electric motor acting as the driving rotor, while the female rotor um, is driven by the male rotor. So only one of them is actually connected to the motor. Now these types of compressors are really useful because they have a high efficiency and high coefficient of performance, and they function more efficiently while operating for long periods of time. Next, we're going to look at the condenser. So as the refrigerant enters as a superheated refrigerant into the condenser coils, it's going to run along horizontal copper pipes that are going to be laid out in orange right here. And as the refrigerant flows through these coils, the fans are going to pull air, cool air from the environment over the coils and disperse the hot air taken from the refrigerant and disperse it back into the environment. And as the refrigerant exits the condenser, it exits as a high pressure, high temperature, saturated liquid. So here's what a condenser would look like. The refrigerant would come in like this. They can either be 2 or 3 pass condensing coils. And what that means is the refrigerant will pass through the coils multiple times in order to remove more heat from the refrigerant. So as it passes, makes several passes, more and more heat is taken out of it. and then it finally it finally exits. Here's an animation of what that would look like. You have the high pressure, high temperature, superheated vapor coming from the compressor, making its passes in the condenser while the fan removes heat from the refrigerant and exits as a high pressure, high temperature saturated liquid. Next, we have the thermostatic expansion valve. Now, this valve operates kind of similarly to a pressure relief valve, but it has a couple more components in it. So one of the biggest components is the sensing bulb. The sensing bulb sits at the outlet of the evaporator and detects the superheat. And inside the bulb is refrigerant. So whenever the superheat from the evaporator boils the refrigerant, um, it creates pressure that goes through the capillary tube into the diaphragm, and the diaphragm expands, activating the pin and pushing down on the spring, allowing more refrigerant to flow through the valve. As more refrigerant flows, the superheat in the evaporator decreases. So the valve repeats consistently to ensure the correct amount of refrigerant can flow through. And the superheat can also be adjusted manually. Here's an animation of what that would look like. So you'd have the high pressure, high temperature saturated liquid coming from the condenser as it goes to the expansion valve, where the sensing bulb is placed at the end of the evaporator, detecting the superheat, expanding the diaphragm, allowing more refrigerant to pass through the evaporator. Now, this animation doesn't show it, but in the evaporator, you would have your supply chilled water going in, and your return chilled water going in, and your supply chilled water going out. Here we can see the shell and tube evaporator. Now this is what you would find previously in the evaporator right here. So as you have in the inlet, you'll have the return chilled water containing the unwanted heat that was collected from the building. The water will pass through the evaporator, and the outlet will be the supplied chilled water at a lower temperature. And the reason it's at a lower temperature is because the refrigerant from the expansion valve at a low temperature, low pressure liquid vapor mixture passes through the evaporator and picks up that unwanted heat from the chilled water, and then the refrigerant will exit as a low temperature, low pressure, saturated or superheated vapor. Here we can see the internal components of the evaporator. So you'd have the refrigerant that flows freely through the evaporator, and the water, as shown previously, the water flows through small tubes inside the evaporator. This is a closed system, so the refrigerant and water never make contact with each other. The refrigerant just picks up the unwanted heat from the chilled water. So now that we know all of the main components, we can look at how that diagram would look with everything put together, starting from your compressor at low pressure, low temperature, saturated vapor, or superheated vapor, depending on the type of compressor being used. It flows to the condenser, where heat is removed from the refrigerant, and then exits at high pressure, high temperature, saturated liquid. One thing that wasn't covered before is the filter dryer. So as the refrigerant passes through there, it picks up unwanted liquid from the condenser and allows it to pass through the expansion valve, and it'll pick up any type of impurity that you wouldn't want going into the compressor and damaging it. Here was what the schematic would look like installed in a building. So you'd have your chillers at the top, where the return chill water in the lighter blue color would flow into the chiller, pass through the evaporator, where it's cooled down, and then it exits as a colder liquid and then it's pumped to the air handling units or fan cooling units, and this is where it's dispersed into the building. Next, we can look at the ideal vapor compression refrigeration cycle. So we have a pH and TS diagram, and we can see how the refrigerant would look and how it changes in phase, going from compression to being condensed, expanded, and evaporated. Next, we have the superheated and subcooled refrigeration cycle. So depending on the preferences of the chiller, it can either be superheated or supercooled or both. And here's what that would look like on the TS diagram. So the advantages for choosing a air-cooled screw compressor would be that they cost less to install because they have less parts compared to like a um, water-cooled chiller. They require less space because they can sit on top of the roof and don't need a mechanical room compared to a water-cooled. This means with more space within the building for business purposes. They also require less maintenance because they have less parts. Um, and the systems are much simpler to design and don't need another set of pumps for the condenser, which would be the water cooled. The water cooled needs an extra set of pumps. So some of the disadvantages would be that the unit is always exposed to the environment. It sits outside, and their fans and compressors will create noise, which the surrounding areas might be able to hear. They don't have long service life as longest service life as water cooled chillers do, because they're exposed to sun, rain, frost, snow, wind, and all those things deteriorate the materials on the unit. They can also suffer from damage, blockage, and recirculation issues. What that means is that the condenser fans, as they are dispersing the unwanted heat, if it's in a confined space that doesn't have good air circulation, it might pull that hot air back through the condenser and not work as efficiently. So when would you want to choose air-cooled screw chillers? You'd want to choose an air-cooled screw chiller if there's a shortage of water, maybe if you live somewhere with a drought or with water restrictions like in California. If you desire a low maintenance cost because there's less parts on it, it's easier to work on. Lower upfront cost because essentially you have less equipment to install. You'd also want to use one if you have a large area open space that's already available, or you can just put it on the top of a building to make things simpler. If you have limited space for a mechanical room, so typically buildings downtown, the lots are very small and they can't just build an extra mechanical room, so they'll use an air-cooled screw chiller and install it on the top of the building. That way it's out of the way and they can still get their air conditioning. If the fan noise and compressor noise is not an issue, then you definitely want to choose an air-cooled screw chiller because you can just put it on top of the building and most likely not even hear it running. And they're also easier and faster to start up. Here are my references. Thank you so much for watching and have a great day.